Probably the most unique and interesting thing about the DFX is the fact that it can transmit and receive signals at two different frequencies, both simultaneously and individually. And that includes both in the discriminating and all-metal modes of operation. So we have a variety of features that allow an operator to select the most appropriate means of using the two-frequency information to get the best possible performance out of the metal detector. And the fact that the individual frequencies can be both individually selected as well as used together to get the best of both worlds, so to speak, is unique to this machine. In order to understand what the DFX is capable of, it's probably useful to start out by talking about what happens as we change the transmitter frequency that we use to interrogate the target in the ground. I'll draw a phase diagram, which we frequently use to indicate signals. And for reference, I'll indicate the targets as they show up on for example, on an XLT or one of our machines that runs at 6.6 kilohertz. The ferrous ground normally shows up in this region. Salt would come in about here, and silver dollars would come at this far end of the scale. And I can put VDI numbers on here to further indicate what these signals indicate. This would be approximately minus 93, approximately plus 5, and about plus 93. And again, these are the numbers that you would see on a machine running at 6.6 kilohertz. Now, if I change the transmitter frequency down to 3 kilohertz, these signals are going to move a little bit. The dollar will come back this way to maybe 80 or thereabouts. Salt will move in this direction and will get considerably weaker. But the ground, fortunately, will stay about the same. If I go to a higher frequency, let me indicate here that the red indicates 3 kilohertz. If I go to a higher frequency, like 15 kilohertz, the salt is going to move in this direction, and the signal may get stronger. The silver dollar will move even farther down in this direction. And once again, the ground will stay in approximately the same spot. So what I can do is I can plot a line that shows the general trend in which targets move as the frequency is changed. I'll indicate that like so. So what happens is that as we increase the frequency, the target is going to move out in this direction, and eventually all targets will arrive in the area where silver dollars normally fall. Okay, next, I think I'll clean this diagram up a little bit and talk about what happens with a particular target as you change the transmitter frequency. I'll use a nickel just as an example. If I go low enough in frequency, let's say I was to go down to maybe 500 hertz, the nickel might appear down in this region. And the length of the arrow that I draw indicates the strength of the signal. And you can see that at a very low frequency, that target will be very weak. Now as I begin to increase the frequency and go up to, let's say, 3 kilohertz, I get a stronger signal, and the phase begins to move out in this direction. If I go up to 6.6, I might be in this region. If I continue to increase in frequency, the target will move out along this line. So what you can see happening is that as we go up in frequency, the length of the arrow that I've drawn gets longer, indicating that the strength of the signal is increasing. But there comes a point where the signal really doesn't get stronger anymore. It merely rotates in phase until it hits this limiting point right here. And that's important because the ground that we balance to is along this axis here. And we want to keep that signal back away from the ground so that we can easily tell the difference between the ground and the targets that are buried in it. So the optimum frequency to pick for a given target is going to be the one at which the signal is strong, and yet it hasn't begun to approach the ground axis where we have a difficult time telling the target from the ground. So for example, for a nickel, 15 kilohertz might be a really good choice. But at that frequency, $1 might be clear over in this range, and we can gain something on the dollar by bringing it back this way by going to a lower frequency. So 3 kilohertz will be a very good frequency for dollars. Now another interesting thing that happens, I'll clean up my diagram again, but as we go up in frequency and targets begin to move out in this direction, if I were to go high enough, all the targets that I care about will get pushed together at this end of the scale, and it becomes very difficult to separate them out and tell one from the other. The same thing happens at this end of the scale. If I go low enough in frequency, all the targets that I care about will get compressed in this range, and once again it becomes very difficult to separate them out. But if I can pick a more appropriate frequency, I can get these targets to spread out. We'll change colors again here. For example, at 6.6 kilohertz, we get a nice spread between nickels, zinc pennies, silver dimes, and dollars. And one of the advantages of going to a higher frequency is that targets such as rings and small gold jewelry items that normally fall in this range will begin to spread out, and it becomes more easy to separate them and tell one from the other. You get better discrimination on targets in that range. By the same token, if I go lower in frequency, my copper and silver coins and targets in this range will begin to spread out, and it becomes easier to tell them apart. So what you can see from all this is that there's clearly no one frequency that's best for all applications. Higher frequencies in general are better for smaller objects, less conductive objects, and lower frequencies give an advantage on things like copper and silver coins, large, very conductive objects. Okay, now this brings me to the DFX and what specifically it offers in the way of new features and capabilities. The DFX transmits and receives simultaneously at these two frequencies, 3 kilohertz and 15 kilohertz. And what makes it unique is we have each of these frequencies available independently, and we can select either one and process signals in the manner in which we've successfully done it for many years by doing ground balancing, discrimination, etc. at either frequency. So the operator can select whichever one he feels is more appropriate for the kinds of targets he's looking for and the ground conditions and such. But in addition to that, the DFX can process both frequencies of information simultaneously. And the way we do that is by first processing them in a conventional fashion. So for example, we'll do discrimination at 3 kilohertz by conventional means. We'll also do discrimination at 15 kilohertz by conventional means. And then our microprocessor will compare the results. And there's a couple of ways that we do this. The first way is to look at the strength of the signal at either of the two frequencies and to pick the stronger of the two. So I'll give an example of that. If a nickel, for example, at 3 kilohertz has a fairly weak signal, and at 15 kilohertz the signal is much stronger, the microprocessor can look at both channels of information and select the strongest signal, which in this case would be 15 kilohertz, and then report that signal to the operator in the form of a VDI number and an audio response. On a silver dollar, on the other hand, at 3 kilohertz, the signal is farther away from the ground axis and therefore gives me a stronger response. So the microprocessor in this case would choose the 3 kilohertz data and report that to the operator and use that one in determining the VDI number. And we call this mode the best data. Where the processor picks the strongest of the two signals. Now, something I should probably mention at this point is what we call normalization. If I pass over a nickel, for example, at 3 kilohertz, I'll calculate a phase and a VDI response that will be at 3K, maybe 10. If I do the same thing at 15 kilohertz, I'll get a VDI response that might be 35. And what the processor has to do in order to be able to perform this operation and have the resulting display make sense to the operator is to convert those numbers to more familiar units. And since on a detector running at 6.6 kilohertz, nickels come in at about 20, the processor then takes the 3 kilohertz data, does a mathematical operation, and shifts that VDI result of 10 and makes it 20. At 15 kilohertz, it takes the result of 30, rotates it backwards, and again causes that to read out as 20. So for the operator, it doesn't matter which frequency you pick, the nickel will always give you a VDI reading of 20. And that is something that can be turned off by an advanced operator if you want to see the original numbers. But that brings me to the next two-frequency mode of operation, which we call correlation. If I pass over the target and the determination at 3 kilohertz gives me a result of 20 after I've done the normalization, at 15 kilohertz if it gives me a result of 20, then I've got a pretty high degree of confidence that that reading is correct. And I'll report that to the operator on the screen in the form of a VDI number and an audio response. If, on the other hand, the results from these two operations don't agree, for example, if at one frequency I get a reading of 10 and at the other frequency I get a reading of 40, that reading will be suppressed. And again, we call this correlation. And these are two of the operating modes that the operator can select. So far we have 4 different operating modes. You can select 3 kilohertz, single frequency operation, 15 kilohertz, single frequency operation, best data mode, or correlate mode. Okay, one thing I want to mention in passing is that the normalization feature, which again is intended for a more advanced operator, can be turned off, and there's a reason you might want to do that. As I mentioned earlier, for example, at 3 kilohertz, targets tend to crowd together in this neighborhood. And if you turn the normalization off, you can see at the other end of the scale, the targets in the silver coin and copper coin range will spread out nicely, and you can see that a lot better if normalization is turned off. If you select 15 kilohertz as your operating frequency, then as these targets begin to spread and move out in this direction, again with normalization turned off, you get a lot finer resolution and you can see the numbers at either end of the scale more clearly. So we think that'll be of some use in the field. Now, so far I've been talking strictly about discrimination and target ID modes of operation, but I want to talk a little bit about the all-metal mode. I started out earlier by drawing salt up here. In a conventional single frequency metal detector, I can be balanced to the ground or I can be balanced to the salt, but I can't be balanced to both at the same time. So consequently, if you go to the beach and you balance your detector to the black sand, you're going to be very sensitive to the salt. If you balance to the salt, you're going to be very sensitive to the black sand. And the DFX has something very useful, which is a two-frequency all-metal mode of operation. And what we do there is we balance the 3 kilohertz signal to salt. We also balance the 15 kilohertz to salt. Now both of them are sensitive to normal ferrous ground or to black sand. But by doing an appropriate scaling and subtraction operation, we can get black sand or ferrous ground cancellation and saltwater cancellation simultaneously. So what you'll find is you take the DFX to the beach, balance to the dry black sand, begin to move down to the salt water, and the detector will remain balanced all the way down the beach. And this is, of course, a very big advantage in all metal in terms of being able to pinpoint targets, measure their depth, and so forth. But it's also an advantage in your discriminating modes because we're using the all metal data to signal to the discriminator the appropriate times to make the target ID calculations. So it should be an advantage in both discrimination and all metal operation on the beach. Okay, so just to kind of wrap this up and summarize, What we've done here is to build a metal detector that can be operated at either of two frequencies in order to allow the operator to pick the one that's best for his application. Or we allow the microprocessor to look at both sets of data simultaneously and pick the most appropriate, as well as having the ability to remain balanced to dry sand and salt water all the way up and down the beach. And I think the combination of these things is going to make this an extremely powerful detector in the field.